I work at Etsy. We've been using ELK for coming up 3 years now. We're trying it out, played around with it for about a year before migrating all our stuff over to it. And so I'm going to be talking about really how to scale it up when you have a lot of data you need to store in it. So first of all, can I get a quick show of hands? How many people here run an ELK stack already? A good number, hopefully. That's pretty good. Okay. We're going to go through a couple of sections. The questions I get asked a lot is, how do I know how big to make my Elasticsearch cluster? How do I know when I need to scale it up? What are the things I need to think about? So we're going to touch on that very briefly. Then we're going to touch on monitoring and scaling Logstash. And after that, we'll go into actually scaling Elasticsearch itself. I do ask, there are two things. If anybody has questions, just raise your hand and ask them. I have about 2 hours worth of content to squeeze into an hour and a half. So hopefully we'll have lots of time for questions at the end if I can rush through it. But if you do have questions, if I skip over something that doesn't make sense, just please ask. The second thing is, at the end, let's discuss the topics. Let's go through all the stuff that we've talked about. And there is a third thing, actually. I have here a number of stickers. And realizing that it's 9 a.m., I want to make sure everyone's kind of engaged and excited. So I'm going to ask some questions as we go through this. And if you get the question right, you can bring the sticker up to me afterwards, and I'll buy you a drink at the bar, beer, Coke, whatever you like. So just a little bit of fun to help us along. Okay. So some of this talk is a little dry. I mean, we're talking about scaling Elasticsearch and Logstash. This is a fairly simple stack as it goes. And I do have lots of graphs and lots of pretty things, but until we get into a sort of about Act 3, about 20 minutes into this, it is a little bit dry, so please bear with me. So Etsy has multiple Elasticsearch clusters. We started with one for our production logs. We started adding more as we started getting requests for specific things, for a cluster to store just logs to do with analytics and so on. So as I mentioned, I have these little stickers. So the first question is, would anyone like to guess how much storage capacity we have in our Elasticsearch cluster? Anybody? Somebody shout out a number. 20 petabytes. Okay, not that big. Anyone else? Anyone? Somebody? How much? Much bigger than that. Somewhere between 20 petabytes and 50 terabytes. 640 terabytes. No, it's close. Actually, I'll give you the sticker for that. So, oh boy, thanks, Clicker. Okay, so our cluster is about 1.5 petabytes, which it's not bad. I think it's a pretty reasonable sized cluster. We've got 300 Elasticsearch instances. They're made up of 141 physical servers, 4,200 CPU cores, ridiculous amounts of memory, and we're indexing at peak about 400,000 log lines per second. This has grown. When we started out doing this initially, we were at about 20,000 log lines a second, just trying to keep things going, and it wasn't enough. And what we found is, as we've introduced this stack, more and more people wanted to keep adding logs to Elasticsearch. So we're actually storing about this much. It ends up being about 10 billion documents a day. So the first thing is, I have some healthy advice for anyone. I know there are a lot of hands, people who hadn't started running an ELK stack yet. This bit is for you. Please, when you start running Elasticsearch out of the box, you install it and it starts going. The first thing it does is it assumes a default cluster name of Elasticsearch. This is terrible. Please change it. Because the moment you start adding more Elasticsearch clusters to your network, if you have multicast, if you don't turn that off, it just becomes a little messy, and it's just good practice. Just change that right at the beginning. Just call it anything but the default. The second thing is, the second option, not having that turned on by default, caused me to lose all the data in our cluster 3 times just by running the wrong delete command. So you can actually set that action destructive requires name to require an index name. It's pretty simple, but it turns out if you don't specify an index name and you send a delete request to the cluster, it'll just delete everything, which is not really healthy. Third thing, always use SSDs. It's 2016. There's no reason at this point not to be using SSDs. If you're in the cloud, you can get them really cheap. If you're buying your own hardware, the prices come down so much. 3 years ago, I would have tried to argue for spinning Rust. I would have tried to say, it's still worth it. In some cases, you can make a case for it, but there's just no reason now at all. And yes, if you're here, if you're seeing this talk, if you're watching it later on, 10 gig networking is going to be a requirement. And you'll see why in a short while. Okay, so sizing up your Elasticsearch cluster. Just a couple of slides here on what you need to think about when you're adding nodes or building your cluster for the first time. When you're looking at CPUs, having more cores is way more important than having clock speed. Even if your clock speed is 50% faster than the number of cores you have, you want more cores. Elasticsearch, Logstash, the whole thing works much better when it can be highly concurrent rather than having fewer numbers of threads and going on faster cores. Memory is going to constrain you. We're going to talk about this in Act 3. Memory is going to be your constraint depending on the number of documents you have and how many shards you break your Elasticsearch cluster down into. You will likely be constrained by your SSD write speed. Now, this is kind of crazy. Like, SSDs are really fast, but we find regularly that we can max out a box with 6 SSDs in it without a problem. You can let Elasticsearch go on that, and it's crazy. And all of these we'll get into in a little while. Okay, there we go. Sorry. Okay, so memory I mentioned, like you're going to be constrained by it. When you're sizing your cluster, you're going to need about 4 bytes for every document that you're storing, and this goes into something Elasticsearch called segment memory. And we will, again, like I said, we'll talk about this a little later on, but if you have about 4 gigabytes of memory, you're going to be able to, across your cluster, you're going to be able to store only about 1 billion documents. And this goes not just for like your current day's index, this is your entire data set. So it's a very quick way of being able to figure out the absolute minimum amount of memory that you need. On top of that, you're going to have field data memory. Field data is data that's loaded into memory by Elasticsearch. It's, depending on how you break your fields down, that's going to require even more memory. Your filter cache, every time you run a search, the results of the filter are saved. That's going to require, we find, somewhere between about 1/4 and 1/2 of the amount of segment memory. If you do a lot of very, very varied requests, it's going to be a lot more, but we usually don't find it goes above about 1/2 of the amount of segment memory that we have. And then after that, the common advice is you want to have at least 50% of your memory free just for the operating system to be able to cache the files off disk. If you can go more than that, it will really help. Like I said, you can't have enough memory. Okay, so disk I/O, and I'm sorry, I apologize again. I'm going really fast through this. There's a lot of content we have to cover. Disk I/O, like I said, sustained SSD write speed is actually going to be a problem when you're running Elasticsearch at scale. It's really, I mean, the SSDs we have can write at about 300 megabytes per second, maxed out, and you have 6 of them in a box. You can actually max out your SATA backplane without a problem when you're doing large reallocations across your cluster. So make sure you're looking at SSDs that are really, really fast. Let's see, I have some calculations on the board. I'm not going to go through these. You guys can take a look at these on the slides later. But really what we're talking about here is how much time is it going to take you to recover if you lose a node in your cluster? And that and network speed really come into play here when we're talking about that. As I mentioned, yeah, network speed. If you have a large cluster, like I said, we have about 1.5 petabytes of data. If you don't have 10 gig networking, trying to do a recovery of, let's say, 1 terabyte of data across a 1 gig network is really, really slow. And we found very quickly when we set up the initial cluster at Etsy, we had 6 nodes and they were all on a 1 gig network. We just found it unbearable. Like, we'd lose a node for hardware reasons, for maybe the box would run out of memory or something, and it would take like 6 hours to recover all the indices on there. It's really just not worth it. Okay, so sizing up your Logstash cluster. The first thing you need to think about when you're trying to figure out how many Logstash nodes is really how much CPU you have. And after you've thought about CPU, go back and think about CPU again. Like, it's the only thing that matters with Logstash. Give it more CPU, more concurrency, more threads. That's it. Okay, we'll come back to Logstash CPU because I have some really good graphs I want to show people. But I want to touch very, very briefly on monitoring. And I promise we're almost through the really dry stuff here. the folks who have an Elasticsearch cluster right now, how many of you are using Marvel to do your monitoring? A small number. How many of you have rolled your own monitoring solution? Oh my God, there were more hands than that earlier. Like, are people not monitoring Elasticsearch? What's going on? So yeah, huh? Using free things is great. But there's a cost. There's always this question of build versus buy, right? We're always trying to figure out, is it better for us to roll our own thing, or is it better for us to just buy the thing from a vendor or from some third party? Marvel is great. I love Marvel. We did use Marvel at Etsy for a long time. Unfortunately, it really costs a lot of money. It's very expensive. But you get a lot for it. We ended up, in the end, rolling our own solution based on just polling the Elasticsearch APIs, which are pretty decent. The Cat API and the Stats API and the Node APIs, between the three of those, you can get almost every metric that you need to for Elasticsearch. There's a lot of information out there on how to query those and how to go through them. I would highly recommend, if you're not going to use Marvel, at least look at this stuff. You can start graphing things like the heap memory used, the number of connections, the garbage collection rates. All this stuff is really important as you scale up your Elasticsearch cluster. If you're running an ELK cluster right now and you haven't explored the Cat API, go do it. Like, that is one of the things that should be second nature to anybody running an Elasticsearch cluster. And then, create dashboards in Graphite or whatever system you like to use. When we get to Act 3 and where I talk about some more benchmarking and scaling things, I'll actually show you how you can do a lot of benchmarking of Logstash using these tools. If you have SSDs, like I said, you really hopefully do. One of the key things to be monitoring is your SSD endurance. A lot of people don't think about this very much, but we managed to burn through about 300 SSDs in 1 year. And when I say burn through, I mean we destroyed the SSDs with the number of writes that we were doing. So having monitoring on the SSD endurance will really save you in the long run. Let's see. There's a little bit about monitoring on Logstash and pipeline being blocked, but we'll get to that. Okay. Disk space thresholds. I just wanted to drop this in here. How many people here are on call at any particular time? Yeah, good number of us. How many of us hate getting paid for disks filling up? Yes. Wait a minute. More hands went up the second time than the first time. What's with that? Okay. So I absolutely do hate getting paid for Elasticsearch disks filling up. And Etsy, we're not in the cloud. We run on bare metal. We have all our own hardware. And so we have a lead time when it comes to buying boxes. It takes us a little time to place an order, get stuff shipped and set up and racked and all that. And so we needed to know, when is the right time to start buying more hardware? When do we need to? And when your disks get 80% full, it's too late at that point, probably, if you're running a large cluster, or 90% or whatever. So we threw together a little calculation and set up some dynamic thresholds for our disk alerts based on the size of the cluster. And what the numbers here are just going through is how many nodes you're comfortable failing in a cluster of whatever size you have, and then calculating how full your disks can be. And that might be handy to some people, hopefully, who are looking to add more boxes. Okay, so thank you for bearing with me. That was the dry stuff. Hopefully the next hour and a bit becomes a lot more interesting. So we'll talk about scaling Logstash first, and then we'll go into scaling Elasticsearch. The first thing, what are the things that really impact the performance of Logstash? And these are the things that we found after running it for about 3 years that really slow things down. And I have some numbers that we're going to go into here. But out of these, I think the two that really came to the top of the list are the first things here, were the line length and the complexity of grok patterns. Elastic give really good advice. They say, if you're running a large system, it's really good to have your logs structured, probably as JSON or something similar. And we'll go into that as well, but line length really matters. The size of the documents that you're passing through Elasticsearch make a huge difference. And I have a feeling that it gets exponentially slower, but I know at least up to 30 kilobytes log lines that we try, they get terrible. So just keep these things in mind as we go through this section. Measure twice. We are going to, yeah, I mentioned writing your logs as JSON. It does help a little bit, but it's not like sort of any kind of holy grail. Logstash internally, when you send it a log line, it has to convert the event from a string to a JSON object internally anyway. And most people I know, even though they are structuring their logs as JSON, they end up doing a lot of parsing on them anyway, extracting more fields, converting timestamps, and doing all this other work. Unless you're actually getting rid of the grok filter completely, just sending your logs as JSON doesn't actually help. I like to advocate actually just having regular text log lines because they're easy to eyeball and read. I hate reading JSON, it's terrible. Wait, does anyone here like reading JSON? Whoa, I saw a hand. Okay, you, at the end of this talk, I'm going to buy you a drink. That's like, you clearly need it. Okay. JQ is your friend. Yes, JQ. Okay, you know what? JQ is the one thing I haven't mentioned in this talk. But if you don't use JQ to quickly parse JSON on the command line, you should really check it out. Okay, so hands up. Okay, so this is gonna be this is the second question. How much does Ruby love creating objects? Lots. You get a drink. All right. Ruby really loves creating objects, and Logstash is written mostly in Ruby. It runs under Java, and one of the big problems you'll find as you're scaling Logstash is, oh my God, every single thing a plugin does creates so many objects, and for the most part, like until you get up to I don't know some millions or billions of documents a day, the defaults are usually all right, kind of, sort of. But you really, like, once you start graphing the number of garbage collections that Logstash is doing, you'll be shocked. Like, it's crazy. Every time, I did a little benchmark here, just showing the number of times, if you run it a million, I ran this a million times, just creating a string, and it took, what was it, 0.13 seconds? 13 seconds. And there are plugins all over Logstash in the community that do this constantly, and they really drag down performance. All this time that's spent is really just creating the objects and then destroying them. So as you get into the next section, plugin performance, keep an eye on. Oh, question. Was that Ruby or JRuby performance? That was JRuby performance. Yes. This was after JVM warm-up time. This was after the JVM warm-up time. Yeah. So it really does, like, I mean, JRuby does do some really cool things when it comes to instantiating objects, but you still cannot do things like freezing strings and things, which I think actually in the latest JRuby, was it 9,000, which Logstash is not using yet, you can do some really cool things with objects and to help garbage collection, but we're not there yet. Maybe in the next year, maybe a little more, we'll get there, but yeah, so you'll see this as, like I said, we're going to plugin performance. Okay, so the first thing to think about, like when we're talking about plugin performance, is what is a baseline? How do we measure what it is we want to do, and measure the changes, right? Like, we don't, as an industry, we try not to just make changes blindly. We always encourage people to measure. So we're going to go through some of the measuring as we work through our plugins here. So the first thing is, as I was writing this talk, I figured that I needed to actually show you guys and go some graphs about what things look like when you make changes. And I didn't have a lot. Like 3 years of work, you'd think I would have some metrics to show everybody, and turns out like most of them I'd lost over time. So I set up this little test bed. And it's actually fairly simple. All I did was I took about 5 minutes of an Apache access log, which is a great thing to test with. Like or like an Nginx access log. It's fairly complex. It needs to be broken down into many fields if you're doing parsing on it. There's a lot of stats you can collect from it. It really exercises Logstash pretty much. And all I did was like grabbed it. I created this very simple Logstash config just to read it in and just spit out a dot for every line that Logstash parses. And I piped that to like a 5-line Python script that reads in the dots and emits metrics to statsd. Everyone here familiar with statsd? Anyone not familiar with statsd? A couple of people. So check out github.com/etsy/statsd. It's a very simple way to collect metrics and send them out to a backend of your choice. We use Graphite, but there's lots of different backends that you can send stats to. And it just helps make pretty graphs like this one. So using that config and sending, I think that file was like about 10 million log lines or something. Just send it through the little script, and it showed that we've got pretty good performance. I think we're looking about 65,000 log lines a second that Logstash can read in and then spit out. And that's all it's doing on this one box, which is not bad for a single instance. So then I threw in Grok. And this graph that I've created is for Logstash 1.5. Logstash 2, there were some Grok changes that really improved performance a lot. Unfortunately, 1.5 is what I'm using right now. So that's what my metrics are on. But I think the principle still holds that when you add in like a simple thing like Grok and you're just filtering, we've got our own custom Apache logline pattern here. It's not really complex. It's the base pattern with like a few other like fields at the end. It actually slowed down everything about 80%, which is crazy. Just based on if you look at this, who can figure out like why it slowed down 80%? It's one thing, and well. And it turns out because I wasn't using any extra workers. It was all single-threaded. Whoops. If you add in more workers, in this case I had a 32 core box, so I told Logstash to use all of them. It brought the performance back up, but it still wasn't great. We're still looking at about 42,000 log lines per second on a single box. This is, like I said, simply the impact of Grok. If you are structuring your logs as JSON and not using Grok, you will have a better time. But most people I know are not doing that. OK, so your baseline is the least amount of work that you can get away with on your Logstash instance. In this case, as we're going through our test, it is just grabbing some logs and just sending them out. You could do this with Elasticsearch. You'd lose some functionality, you'd lose some cool stuff, but that is your baseline. OK. Scaling Logstash, when we're talking about plugins, there are lots and lots of filter plugins that the community has developed over time. KV is one of them. We started using KV pretty early on because it's really convenient in splitting up fields into key value pairs and making it easier for you to search on your log lines later on. And what we found when we added it in was that it actually dropped performance even more, like taking just that base filter speed with Grok and adding in KV just knocked off like 10% more of our performance. And going back from that initial 65K when you're trying things out, hey, this is great, down to, OK, now I'm using all my CPU cores and I'm at like, we're looking at about 40,000 events per second, it really starts hurting. It was about this time, probably 2 years ago, that we started to write our own plugins. And this is like one of the best lessons that I think, give everybody. If you take one thing away from scaling Logstash, it's that please don't be afraid to write your own plugins. A lot of people don't like doing it. Well, now we have to maintain them. Now we have to worry about like what they're going to do, how they're going to be compatible in the future, and things like that. Don't be afraid. We got rid of the KV plugin by replacing it with something like this, and which we called Split KV. And all it was doing was taking some fairly structured fields, for example, like a query string off a request line, and instead of using regular expression scan as the community KV plugin does, it was just calling split a whole bunch of times in Ruby. Turns out it's a lot faster if you do that. In this case, our Logstash instances went from about being 100% busy to being about 33% busy. So just doing little things like that can make a really, really big difference. The plugins that you see, that you get from the community are really written for the general case. And you'll find as you scale up that it is much more efficient if you start writing your own plugins for very specific use cases that you have. So really think about that as you scale up. OK, I'm making really good time. I might actually get 2 hours of content done in 90 minutes. OK, so the next thing would be the Elasticsearch output. This is the next thing that we found caused us to have bottlenecks in the system. By default, the Elasticsearch output plugin, I think it's changed a couple of times, but the latest iteration of it, when it's spooling events to send in bulk to Elasticsearch, I think it collects about 500 at a time. I think the number used to be a little higher. It's kind of gone back and forth, and we've settled on 500 for the default. But that's actually really slow when you're running at scale, especially if you have a large Elasticsearch cluster on the back end. 500 we found was definitely not enough. And there are a couple of other settings in that plugin that do make sense to tune. Idle flush time by default goes to 1 second. We found it more helpful to have that increased to about 5 seconds. And this is what we found happened when we increased some of those settings. So the first thing we did was we increased the number of workers. We started with the default workers of 3, and we increased the flush size to 5,000. We got a pretty good boost there. And then from there, we kept increasing the number of workers and the flush size until we got to some high limit. What you see at the very top, though, you see we got more performance. There was a big dip in the middle, and that's just down to garbage collection again. So garbage collection is going to be something that, as you scale, is going to, like I said before, it's going to cause you problems. It's going to be something to keep an eye on. But with the Elasticsearch output, as you grow, just start playing with those numbers first and see where you end up. Pipeline performance is kind of an important thing as well. This became tunable, I believe, in Logstash version 2.3 more easily. So internally, between the inputs and the filters, and between the filters and the outputs, Logstash has a Ruby-sized queue, or in JRuby, I think it's just a standard queue. But that queue is limited to 20 events. And this is done on purpose because if you have events that are mid-flight, that are going from your inputs to your outputs, and you've already acknowledged at the source, like to Lumberjack or whatever, or Logstash forwarder or whatever is forwarding your logs, that you've received the events, and then Logstash crashes, you can lose those events that are mid-flight. So that number is kept low on purpose, but the problem is that it really slows down performance. It limits how much you can actually shove into this pipeline and from your inputs through to your outputs at any one time. And we found we had pretty good performance improvements, especially if we increased the size queue from between the filters and the outputs. Unfortunately, if you're not on Logstash 2.3 yet, you have to go in, you have to edit the pipeline code in your installation. It's not hard to do, it's just 2 lines of Ruby. But if you have Logstash 2.3 already, you can just send this pipeline batch size switch when you start up Logstash, and you'll probably notice a decent improvement there. Okay. So I talked a little bit about some of these changes that you want to make. What's a good way of testing that your changes are actually going to work? And this isn't so much to do with performance, but I really wanted to throw this in because it's a question that we get asked regularly, fairly regularly. How do you actually test that your configuration changes with Logstash are going to work? The way we do it is by adding context to our log lines. We add at the beginning of our Logstash config. We have 2 things. We add an index time, which is the time at which Logstash saw the event, which is going to be obviously different from the source timestamp that was in your log line. And what this helps you do is figure out if you have latency in your pipeline between logs being generated on disks somewhere else and logs being processed by Logstash. You can add a third one if you want for timeline for when ingested into Elasticsearch, but this is something that can be really useful to help graph if your things are actually reducing latency. And the second thing we just kind of like to add ourselves is an extra field just to know which Logstash server parsed any particular log line. It comes in handy when you're trying to figure out why did this thing not work on this one box. There was a third thing as well. We have a plugin which we are open sourcing today called HashID. It's a very simple plugin. It's about 10 lines. But all it does is it creates a SHA-1 hash of your message field and uses that as the ID to Elasticsearch. Logstash does have a community plugin called UUID, which is supposed to do something similar, but it doesn't quite do the same thing. UUID generates kind of a random ID. In this case, HashID is generating a consistent ID, so that if you ever replay your logs, if you want to just throw the same logs into Logstash over and over again, maybe because you're missing events, maybe because you're doing some benchmarking, HashID comes in really handy because Elasticsearch using the same the same ID each time won't create lots of duplicate events. It'll realize you're sending the same log line in. So if you go to github.com/etsy/logstash-plugins, there are a handful of plugins there that we use internally, which you folks might find handy. Okay. All right, I should probably slow down a little bit. Am I going too fast for everybody? No? Everyone good? All right, okay. All right, so those three things that I mentioned, adding the hash ID and the two extra fields, they cause us to take about a 10% hit. But in this case, we're actually pretty happy with that. Like 10% I think is a small price to pay to get that little bit of extra context and reliability. The second thing that we do when we're testing Logstash changes is to use server spec. We use Chef and for our configuration changes, and we throw in some server spec to help us figure out if a change we're about to push is actually going to work or not. This is our server spec configuration. It's kind of, I don't know how clearly you guys can see that on the screen, but it's fairly simple. All it's doing is it's checking if Logstash is installed, if Chef client ran successfully, if the Logstash internal configuration check passed, and then it's piping like 4 lines, an Apache log line, an application log line, and like a few other log lines through a very, very basic Logstash config that looks kind of like this. Just taking it, so that's the input. It's reading it in and then passing it through these kinds of filters. And that way we can have some reliability that if we're making a change, that we're not actually breaking our parsing or anything else that we care about. So if you're making changes, this is a quick and dirty way of doing unit testing with Logstash. It might come in handy. Especially if you're trying to deploy a change to like 50 Logstash servers at the same time. All right, so okay. So in summary for Logstash, more CPU cores over clock speed, increase in the pipeline size. Memory, I didn't mention memory too much for Logstash, but as you increase the pipeline size, you're probably going to want more memory. We give each of our Logstash instances about 18 gigs. We have 14 in our 14 Logstash instances in our production cluster now. And this seems to work fairly well. That's something that you have to play around with. It scales very well horizontally and benchmark everything. Okay. Slide 57 of 120, almost there. Okay. So scaling Elasticsearch. This is I think sort of the meat of the talk, the more interesting stuff. So as we did with Logstash, let's establish our baseline first. We took Logstash. I took the same tests that I was running with Logstash, using that Apache log file with about 10 million log lines in it, and just started piping that through to Elasticsearch, doing just very basic processing, just grok, which was extracting maybe about 20 fields, and sending that to Elasticsearch. And our performance, when we were last looking at it, I think it's about 42,000 log lines a second that Logstash was processing. Sending it to Elasticsearch actually drops that down to, oh goodness, like less than 10,000, I think. Is that right? Yeah, that was about right, less than 10,000. So that's a pretty big drop, and that indexing is really spiky as well. Like that's not steady as I think most of us would really like it. So in Elasticsearch, what impacts indexing performance? All right, I'm going to open this up a little bit. So throw out some answers if anyone's comfortable with this. What things do you think impact indexing performance the most? Turning it on impacts the performance a lot. You get 2 stickers for that. Alice, thank you. Anybody else? Like what else? What are the main things that should impact indexing performance? Disk I/O and I/O weight are probably the biggest things. If you're running an Elasticsearch instance with any amount of I/O weight, and it's like 2 slides on from here, but any amount of I/O weight, like Elasticsearch hates it. We had systems that had probably about 2 or 3% persistent I/O weight, and it was terrible. Like the performance of those was noticeably bad. So that was the first time when we started our Elasticsearch clusters at Etsy, we were using spinning disk, and it was the switch from that just to not having any I/O weight was incredible. Line length, as I mentioned in the Logstash parsing, Logstash has, if you're using plugins like KV or anything else that does regular expression scanning, long line lengths really impact its performance. The same thing's true with Elasticsearch. When Elasticsearch has to do analysis or storage of long log lines, it impacts it pretty badly. Doc values are a thing. For the folks not using Elasticsearch yet, Elasticsearch uses Lucene on the back end for its storage and for searching, and the way Lucene stores the data on disk is in an inverted index, so that it's easy for it to look up and find specific tokens, specific words very quickly. It's a text search engine. It's really, really good at that. Unfortunately, one of the downsides is that when you try and search a field in Elasticsearch, going back to sort of pre-2.0 Elasticsearch days, where doc values were not the default, Elasticsearch and Lucene underneath have to load up a lot of stuff into memory. Doc values came along as a way to, instead of having to store lots of field data in memory, it could actually just be stored in disk, on disk, so that you actually have to pull less into memory and it's a little faster. But turning doc values on, and it is on by default in, I think from Elasticsearch 2.0 onwards, does have a hit on indexing performance. It's actually gotten a lot better in 1.5, Elasticsearch 1.5, it was pretty bad. In 2.0, it got a lot better. I think in 2.3, it's actually, the difference isn't huge, but there is definitely a difference there. Uses more, not just more CPU time, and of course, because you're storing stuff that would otherwise be loaded into memory on disk, it's going to use more disk space. The advantage is that it does help you avoid out-of-memorying your Elasticsearch instance. So we'll go into the balancing act for doc values in a few moments. And like I mentioned like 3 times already, like network bandwidth is a big deal. More is good. CPU. Another like there's 2 more things on this slide. Mappings, the default mapping in Elasticsearch, again, for those not running an ELK stack yet, the mapping is kind of like a schema in an SQL relational database. It just defines the type of a field, whether it's a string, an integer, a long, whatever you're working with. The default mapping that comes with Logstash, that Logstash uses with Elasticsearch, creates a ton of extra fields. And that has an impact on your indexing performance, along with merging that Elasticsearch does and any concurrent recoveries that are happening. All of these things we're going to go into in a few moments. The other things that impact your ability to index quickly, how much memory is allocated to index buffers. By default, it's actually a fairly low number, and Elastic do recommend increasing it. Garbage collection, not so much a problem these days, but if you're running anything before, if you're running one of the earlier Elasticsearch releases still, we found that to be kind of painful, and networking. Okay, memory. So out of all of the for all the Elasticsearch instances that we run at Etsy, we allocate 32 gigabytes of memory for each one. There's reasons with the JVM, if you're not familiar with the way the JVM allocates memory, there's reasons why you cannot go over 32 gigabytes on a 64-bit instance. I can go into that if anybody would like me to. But we sort of find that this balance has worked very well for us. Field data ends up taking, question. For this testing, yes, I was. In production, no, we're not. So in production, we're still actually using ES 1.5.3, I think. And upgrading is a thing. There's oh, good, I'm not the only one. Phew, okay, yeah. Yes, do upgrade. Like if you're not on Elasticsearch 2.0, we are in the process of upgrading. But it's a thing. Like upgrading Elasticsearch major releases, you do have to be careful, and it takes a little bit of time and patience and care. But yeah, so all the benchmarking I did here was with Elasticsearch 2, but in production we are running 1.5 point something, the latest 1.5. So an example memory distribution, we find that about 10% of our memory ends up being used for field data, which I mentioned before, if you are not using doc values on a field, which hopefully by the end of this talk you won't be, you end up pulling a lot of things into memory, and that ends up consuming about 10% of our heap. Filter cache comes into play when you do searches. It's the results of, for example, Kibana running filters on your searches. Elasticsearch caches those. And index buffering, this is the one thing that we actually set a hard limit on of 500 megabytes. I'll be honest, I don't remember what the default is these days for Elasticsearch's index buffer, but I believe it is quite a bit less than that, unless anyone would like to correct me. The index buffer is used when Logstash or whatever application you're using is sending documents into Elasticsearch. They get buffered in memory before they're actually flushed out to disk. Elastic's testing found that taking that up to about 500 megabytes has benefits. After 500 megabytes, there's really not much of a benefit. So having that in place really does impact the rate at which you can at index. I mentioned at the beginning when we were talking about scaling your Elasticsearch clusters that you need about 4 bytes-ish for every document that you want to index. This goes into something called the segment cache, which is, again, it's in memory, and it's a fast lookup for Elasticsearch to figure out where particular documents are, which segments they're in on disk, and that's about roughly how much you'll need. And after that, once you know that, you can then start calculating how many documents you can start storing per Elasticsearch instance. So in this case, I did a little calculation. If you have 10 billion documents a day and you've got 200 shards, and this works out to about 50 million documents per shard, depending on how many shards you have per day, it'll help you figure out how much data you can actually retain. The more documents you have, the more daily shards you have, the more you need to sort of split up how much you can retain. All right. Yes. 200 total shards, I believe. Good question that I should know the answer to. I think it's total because Elasticsearch does do searching on replicas as well if primaries are unavailable and so on. So. Scaling Elasticsearch. So doc values. We mentioned this thing about how Elasticsearch, when it's storing data on disk, doc values came around because people were storing a lot of fields on disk, and when you're trying to search, across one field across, I don't know, like I said, there's 10 billion documents, it requires loading a lot of these documents into memory in order to try and figure out where all the data is and return it. Doc values help reduce this. I think Elastic's documents say that you can go down to running Elasticsearch with like a 1 gigabyte heap or something. We tried it, we couldn't get it down to a 1 gigabyte heap. For us, it was impossible. But doc values do help. The problem I find with the default sort of out-of-the-box configuration for Elasticsearch and Logstash is that they create doc values entries for everything. And in this case, we did turn on doc values for everything. And then 2 days later, we found our cluster ran out of disk. And I was like, what is going on? Like there's no way this cluster should run out of disk. And it turns out that the on-disk storage, like for 1 day for a particular shard, went from 1.7 gigs to like 100 gigs, which is nuts. But what we learned from that is that you don't need doc values enabled for every single field. If, for example, you have an application and you generate a lot of key value pairs in your logs, maybe your developers are going to search on 1% of those, 5%, 10% of those, and they're fairly small, and maybe they're not like in every document. Just turning on doc values everywhere, it just consumes a lot of disk when everything else wouldn't actually take all that memory in the first place. So what you can do is you should monitor the output, and this is another thing that you can, if you're rolling your own metrics, you should capture and graph the output of the field data, the cat field data API, and it will tell you something like this. It'll show you across your cluster how much memory each field is taking, each field that is not doc value. So in this case, I've got Just a couple. I've got a size field, a request URI, I've got an owner field, and an IP address field. And it's showing me like per node. So each of these lines is one Elasticsearch cluster, one Elasticsearch node in the cluster, and it's showing me how much memory, field data memory, is being taken on each one. So this is super helpful in figuring out which things you need to convert from not using doc values to using doc values because you're using too much memory. And we'll talk about mappings as well shortly. So Elasticsearch's memory requirements, like I said, we run, our clusters usually have about, each node in the cluster usually has about 128 gigs of memory, mostly because it's convenient for us to run that. I know some other companies using larger instances, 256 gigs of memory. The nice thing is you can run multiple instances of Elasticsearch per physical server or virtual server. And Elasticsearch handles that really well. Just give each one about 32 gigs of memory, things will be great. There is a little bit here that I wanted to talk about. Depending on what kind of hardware you have, and whether you have like Haswell or Skylake CPUs or which specific iterations of those you have, the CPUs have different numbers of memory channels. So if you're buying your own hardware, we actually found we got I think I want to say about a 10% improvement by making sure that we had the correct number of DIMMs allocated per physical CPU. In the case of the latest iteration, the latest hardware, I want to say most of the CPUs have 4 memory channels, so make sure you have DIMMs in multiples of 4 across your hardware. It's just one of those little things that can actually help your performance. Okay, so Elasticsearch CPU performance. Most of the stuff that Elasticsearch does is fairly CPU intensive. When you're indexing, it needs to do analysis on your log lines. It needs to merge those. Merging. How many people have had to deal with merging issues in Elasticsearch already? One person. One person. 2 people. Okay. So actually, I'll talk about this a little bit briefly. When you index into Elasticsearch, the data doesn't go into a single large file on disk immediately. It's written to a segment on disk, which is a new file which takes up to a certain number of records. And when Elasticsearch finds that it has enough of these segments, it merges them together into a larger segment, and it keeps going like this, creating larger and larger segments. One of the things you can do as a nightly operation and is recommended by Elasticsearch is to run an optimize on your index, which brings however many segments were created over the day and merged up into like 1 or 2 segments. It improves, it reduces memory, it improves search performance, does a lot of stuff. But merging is this activity that has to happen on a fairly constant basis as you're indexing new things into Elasticsearch. So a lot of CPU goes to that. Then you have some more that goes into, if you're doing aggregations in Elasticsearch, some of the CPU goes there. And compression, decompression of data on disk, which is not something you can avoid too much. If you have a very write-heavy workload, which for most of us, if we're talking about the ELK stack, you're writing much more than you're actually reading off disk. The number of CPU cores, again, Elasticsearch loves concurrency. Having more CPU cores is a lot better. Okay, so let's talk about that baseline. This is that really spiky performance that when we tried to index those 10 million log lines from Logstash into Elasticsearch, this is what we were getting. So why was it so slow? Like, what was actually being the holdback here? It turns out that little thing I mentioned a moment ago, merging, really, really sucks. As you scale up, you will undoubtedly run into this problem. There are some things you can do. You can increase the shard count, which helps Elasticsearch a little bit, running more merges concurrently. You can also, if you're running an Elasticsearch instance before 2.0, there is an option called index store throttle type, which needs to be just turned off. Like if you have SSDs, this thing needs to be set to none. In Elasticsearch 2.0, The reason this needs to be set to none is that by default, Elasticsearch limits the rate at which it does merging to something fairly slow. I think like 20 megabytes a second of writes before 2.0, like I said. If you are still running something older than that, turning this off lets merges run a lot faster, and merges will then not block your indexing. If you're running something newer than 2.0, you don't have to worry about it. That setting became, actually, I think you do need to set that to none, and then the rate, which was defaulted to 20 megabytes, became dynamic. So do set this to none in any case. So it was still running kind of slow, and as I was running this testing, I realized one thing: don't run Logstash and Elasticsearch on the same box. It's not a good idea when you're trying to scale things up. So I split the hosts out. We went from, what are we looking at here? About 15,000-ish log lines a second, freeing up just the impact of CPU is really highlighted by this. When we're looking at a box being completely maxed out and splitting the nodes so that I'm running Elasticsearch on another box, it's again just consuming 100% of CPU as I'm doing indexing, and Logstash is like grasping for like 40%. That log line, that performance went up from about 15,000 to about 20,000-ish. So CPU is super duper really important. Another question I had when I was trying to scale up this cluster was, does hyperthreading in your CPUs actually help? There's like nothing out there. Like if you try and figure out if people are running Elasticsearch with or without hyperthreading, there are instances where certain applications run better with hyperthreading turned off. In this case, hyperthreading really, really does help Elasticsearch. It counts for about 20% of performance. I'm just going to skip back a couple of slides, and I want to kind of highlight this slide a little bit. You see Elasticsearch taking up 100% of CPU time. It's taking up all the CPU cores, including the hyperthreading cores. Logstash, on the other hand, isn't. Logstash actually doesn't benefit from hyperthreading. It's not generally bottlenecked on I/O or other operations. Turning off hyperthreading can, depending on kind of what you're doing with Logstash, get you a little bit more performance. That is one case where I would recommend everyone try out turning hyperthreading off if you're running on bare metal and you have that option. But otherwise, in Elasticsearch, definitely sort of make sure everybody knows hyperthreading is actually really important. Okay, so what else helps? And you probably just saw the next slide. Whoops. CPU scaling governors in Linux, if you're running on a Linux system, do help. By default, at least, my experience is mostly with Red Hat and CentOS and Fedora. They, by default, use PowerSave as a CPU governor, which is nice. It helps you save some trees. We all like trees. But it does reduce the performance. Changing it to using the performance scaling governor does get you a little bit more. In this case, the benchmarking I found got us about 15–20% more performance. And I'm not sure if this is true for cloud environments like Amazon, Rackspace, DigitalOcean, but I would recommend that people try this out and try changing your CPU governor if you're able to, and see if you can squeeze out a little bit more performance. Okay, so Elasticsearch storage. I'd like to tell you a little story for a moment about SSDs. I mentioned that in the first year we burnt out 384 SSDs. It was really, really easy to do because we initially were building out a prototype cluster, and so we bought cheap SSDs. They were consumer-grade Samsung 840 EVO drives, which was possibly one of the worst mistakes we could have made in terms of storage, because what we found when Elasticsearch got really, really busy was that I/O weight would go up, it would be there for a little while, and then the entire cluster would come crashing down. It's terrible. Like I mentioned, 2 or 3% of I/O weight. Like when it happens persistently, Elasticsearch just kind of just gives up. Says, I don't want to deal with this anymore. So buying enterprise, if you're using SSDs, having enterprise-grade SSDs, very, very important. And if anyone would like to talk to me at the end, I can give you really good advice on what specific things to look for in SSDs. So the common advice that Elastic and everyone else talks about, use SSDs, use RAID 0. Software RAID is good enough. You don't have to have like hardware RAID, it's only RAID 0. Hopefully you have replication turned on in Elasticsearch if you're using RAID 0 so that you're not losing data when a box goes down. But that's the common advice, everyone kind of does it. The uncommon advice, like I mentioned, good SSDs make a big difference compared to cheap SSDs. The write rates and their endurance really make a difference. Elasticsearch has an option where if you don't want to use RAID 0, you can specify multiple paths to different disks in the path.data option. And it's nice. It kind of gives you a little bit of comfort, like, okay, well, if I lose a disk, I'm not losing everything. And Elasticsearch did make some improvements recently where a single shard on a node, if you're using multiple data paths, will live on one disk. So if you lose a disk, you're going to lose a whole shard, but you're not going to lose multiple shards necessarily, or all your shards. The downside of that is Elasticsearch also has a translog, which is kind of like a write-ahead log, where it puts everything kind of like a journal. It puts all the writes down initially into the translog, and later they're put into those segments I talked about and then merged through into other things. If you happen to specify multiple data paths, the translog at any one time will be on one disk. It will not be striped across multiple disks, and it will rotate which disk it's on. So if you happen to do that and you're indexing in a really high volume, you're wondering, why is the first disk really slow? Oh, it's fast again. Why is the second disk really slow? It'll be things like this. So if you can help it, just use software RAID 0, LVM, MD in Linux, whatever you like. zpool on ZFS, wonderful things. There is the ability in Elasticsearch to reduce the durability. By default, all writes cause an F-sync on disk, which if you have SSDs is not so bad. It's still a hit, but you can turn that off by switching the translog durability to async, which will cause Elasticsearch to only run an F-sync on the translog about every 5 seconds by default. Which, if you're comfortable with losing up to about 5 seconds of logs, may not be so bad, and it can actually help squeeze out a little bit more performance. And again, if you have replication turned on your cluster, this can be a really nice, cool way to get a win. Cluster recovery really eats up I/O. So I mentioned right at the beginning of this talk, we have no problem at Etsy like maxing out the SATA backplane on our servers just by reading data off disks. It happens all the time. We pull out a node or two nodes out of a cluster, or we tell Elasticsearch, evacuate all the nodes off of this machine, and it'll just go full speed as fast as it can. We just let it go. And so being able to tune that a little bit can be helpful. We find that when we're doing cluster recoveries with Elasticsearch, we usually need to tune at least the max byte rate that we're running at. In some instances, you'll find that, okay, you're only migrating data between a few nodes, and you can go a little faster, and it's okay. Maybe you're not going to max out your network. In other cases, if there's a large sort of cluster-wide recovery that's happening, maybe you need to throttle this down a little bit. Getting comfortable with tuning some of these variables is very handy. Doing it before you're in the middle of a fire is even better. Okay, I already talked about choosing your SSDs wisely. Consumer-grade SSDs do have slower writes. They have slower sequential read and write rates, random read and write rates. The big thing about them is that they do have lower endurance. They're not really designed to have large numbers of writes happen on them. We started with the Samsung 840 EVOs. We've moved on to some better enterprise-grade drives. When you're looking for SSDs, the things to look for, there's sort of three classes of SSDs that the industry talks about. There's read-intensive, mixed-use, and write-intensive. For most cases, we find that with ELK, a mixed-use drive, mixed-use SSDs are pretty good. They have a good balance between write endurance, sort of roughly in the 10 drive writes per day range, which we don't quite hit yet, but we probably will soon. And they have pretty good balanced read-write performance. So I mentioned that the fsync tunable, the reduced concurrency, the reduced durability on your translog is a thing. How much does it help? So this was the last thing that we looked at when we were doing our indexing in our graphs. This will be the new baseline that we're going to talk about going forward. I turned off the durability, and this happened to the graph, which is pretty good. Like, I think steady, more smooth indexing is a lot better than really, really spiky indexing all the time. The performance stayed roughly the same, but it was a lot smoother and a lot more predictable. So the performance improvement, it wasn't huge. I kind of hoped when I was going through this testing that we'd get a bigger impact out of reducing the fsync rate. So why was it smaller? One guess. Anybody? No? Okay. It was merging again, which is really, really terrible. Elasticsearch has a hot threads API that you can take a look at, and it will tell you what the top 3 threads of every Elasticsearch instance are doing at any one time. Very handy if your cluster's slow, if you're trying to figure out why things are so busy and you can't figure out where your CPU is going. Hitting this hot threads API can reveal a ton of stuff. In this case, I just did a little grep to see where the percentage of CPU is going, and every single Elasticsearch thread bar 1 was going towards merging. All right, so we'll get back to fixing this merging in just a moment. I think I've talked a lot about SSDs at this point. I hope is everybody here going to use SSDs for Elasticsearch? Yes, I see lots of, is anybody not going to use SSDs for Elasticsearch? Nobody, thank you. Okay, my job is done, I can go. There is one other thing that can really help when it comes to your storage, and this is a pattern we developed about 3 years ago when we were starting to work with Elasticsearch. It's nice to have lots and lots of memory, lots and lots of disk, lots and lots of CPU for all your Elasticsearch instances, but it comes at a cost. We're all working in businesses where we do have to be mindful about money that we're spending. Nobody has a blank check. And one of the things that you can do is take a look at where most of your searches are running. Are people in your organization searching data over the last day, or the last week, the last month? And how much retention do you want? In our case, in ELK, we retain about, in our main ELK, our largest cluster, we retain about a month's worth of data. And most of the searches, more than 90% of the searches happen on data over the last week. So what we do is we take everything older than a week and we migrate it onto other machines which have much larger SSDs, but we can squeeze more data onto them. So kind of like per search, you're getting a little bit less performance out of these boxes because they have to search through more data on disk. But you get a lot of benefit because now you've not only freed up more space on your front-end clusters, your first-tier clusters, you've also reduced the memory footprint that those boxes need, and they can focus more on searching the more recent data. So having sort of multi-tiered storage can be a pretty big benefit. Okay, so this merging thing. Why does the default configuration in Elasticsearch cause so much merging? You may be able to see it here. If you've looked at Elasticsearch mappings before, you will likely need to be able to create your own mappings as you scale up. This is the default one that ships. This is part of the default one that ships with Logstash. And the bit that's causing a lot of merging in this case is that every single field is analyzed, and every single field creates a second field called fieldname.raw that isn't analyzed. So again, for those who aren't running Elasticsearch yet or who aren't familiar with Elasticsearch analysis, when you send a document to Elasticsearch, when it's looking over the fields, it's parsing the fields to store them, it can either run analysis on them or not. Analysis is the process of creating tokens from your field. So if you have a field and it's a string that says scaling Elasticsearch default mapping, and you tell it to run through the standard analyzer, it's actually going to break that down into 4 tokens: scaling, Elasticsearch, default, and a mapping. This is nice because you can do a search without having to know exactly what your string looked like. When you're searching using a text engine, it's a text search engine. Just giving it a word and letting it find that word anywhere in your documents is really kind of what we want. But doing it over every single field can have a really negative impact. We, in our mapping, allow analysis to happen on the message field, and the message field is the default field that's searched by Kibana when you're doing searches, so that free-form text searches still work. But you can specify, if you specify a particular field name, you are looking for exact contents. And in this case, we changed our own mapping to look something a little bit like this. I do have a link. I think I have a link at the end of this talk that has an example mapping that you can send into Logstash, which will exhibit this behavior. You won't have free-form text searching across every field, but if you're comfortable having it with just sort of the default message field, and then doing more exact searching on the other fields, you can reduce merging quite a bit. That actually, in my testing, turned out to be a small help, not a huge one, mostly because I'd already maxed out the box. I apologize, I don't have a better graph for that. But that's where you just kind of need more Elasticsearch boxes. So talking about indexing performance, there are some more things that you can do. Elasticsearch has multiple thread pools, and these thread pools are used for indexing, for searching, for merging, for a lot of other operations, pretty much everything that Elasticsearch does. And by default, Elasticsearch assigns however many CPU cores you have in your box. That's how many threads you get in the bulk thread pool, in the bulk indexing pool. In addition to that, it has a backup queue, so that, for example, if you're working on a box with 32 CPU cores, you'll have 32 bulk threads to do your indexing. But if you try and index more than that, if all those threads are busy, your request goes into a queue. That queue, by default, is sized at 50 requests, which, if you're running through, I don't know, any kind of pretty intensive bulk indexing, it's really easy to hit that, max out your bulk threads and hit that 50 queue limit. And more often than not, what we found is that you end up, when you're doing bulk indexing, especially from Logstash, but if you're using any application that's throwing just a ton of data Elasticsearch, you're not frequently going to max out those bulk threads and stay maxed out for a sustained period of time. You're going to end up throwing a lot of data at Elasticsearch, and then Logstash is going to parse a lot of stuff internally, and then throw out some more at Elasticsearch, and then parse some more and throw it out. It's this very up and down sort of thing on a graph. And it's super easy to max out the number of bulk threads, but then it also becomes super easy to max out the queue behind that. If you do max out the queue, Elasticsearch will start rejecting indexing requests. So Elastic, in their documentation, don't generally recommend increasing the bulk queue, because it is usually an indication that you have a bottleneck somewhere else. But we find that increasing that from 50 to about 250 in our case helps smooth out performance, because we're not throwing things at Elastic at a very smooth rate. They're throwing these bulk events every second or every half a second or every quarter of a second, whatever it is. It lets Elastic buffer all of those and process them before the next batch come in. So it can help increase indexing performance a reasonable amount there. I already talked about the index buffer. Increasing that to 500 megabytes is a big deal. Again, another thing, by default, Elasticsearch, when you create an index and you index documents into it, those documents don't become live. Those log lines don't become instantly available. Elasticsearch has to do a refresh operation, which happens out of the box. It happens every 1 second, which is very frequent. If you're doing a lot of really, really fast indexing, Elasticsearch having to stop and refresh the index and make all that stuff live is a big deal. So reducing that a little bit, 5 seconds seems to be a good balance and it is something that also Elastic recommend. Works well. Spreading your indexing requests to multiple hosts. If you have a cluster with 5 or 10 or 20 or 50 or however many Elasticsearch boxes you have, and you have also multiple Logstash servers, don't send all of those requests for indexing to the same box. You're going to max out its network bandwidth. You're going to max out some of the resource that it's using to then distribute those documents across the cluster. It's much nicer on the cluster if you spread that indexing out. Yes, absolutely. So the question was, do search nodes help? Having dedicated nodes that do searching, that don't store data, that don't do indexing. Yes, actually having, we have in our clusters, we have in our main cluster, largest one, we have 2 nodes which run Kibana, and they're part of the cluster, but they don't store data. We don't send indexing requests to them. All they do is searches, and it does help a lot because those boxes can then use their memory for storing results. If you have a query cache and other things, that will definitely help a lot. In our smaller clusters, we don't have that because we find sort of the trade-off between having extra boxes to manage and the cost of running those is just not quite there. But you will certainly likely run into a sort of a tipping point where having those can be a big benefit, yes. Increasing, as I mentioned, the Logstash output, increasing the number of workers until you stop seeing improvements. In our case, we run half the number of CPU cores. Seems to go pretty well for us. And the flash size and the disk I/O performance. Indexing performance, there is one other thing I want to make note of. In Elasticsearch in Logstash, I think 2.0, the default output for the Elasticsearch plugin, I think, changed to HTTP. And at the time, the HTTP output wasn't as fast as using the node or the transport option. It has gotten a lot better, at least in the little bit of testing I've done with Logstash 2.3 and Elasticsearch 2.0, there is still a slight performance benefit, maybe about 10 to 15% of if you're using the transport protocol option instead of HTTP. But it is definitely nicer if you can use HTTP. It'll be it's a little nicer because your Logstash instance doesn't have to be tied to a specific Elasticsearch version and other fun stuff. But if you need to eke out a little bit more performance, you're still struggling on the Logstash side, try using the transport protocol. The node protocol, I'm not a big fan of it. It worked okay when we were running a much smaller cluster, but when Elasticsearch, when you set up your output to use the node protocol, Logstash then has to establish a network connection with every Elasticsearch node in your cluster, and it's actually it's a bit of a headache to try and manage that. Then when your Logstash node drops out of the cluster, every node has to realize it's happened, and try to avoid using the node protocol if you can. I mentioned a few times this idea of the mapping and having your own custom mapping. It's something that is definitely worth getting comfortable with. We have one it's not very long. You can take the one that comes with Logstash and tweak it up and just apply it as a sort of the default template. But it can really help you a lot with your indexing performance. The first thing we did was take out all the raw fields, so Elasticsearch is doing less work in having to create all these extra fields every time we index a log line. Those extra fields, the extra, by default also, like I mentioned, all these fields are using doc values. So you're eating up a lot of disk space, you're eating up disk I/O. And doc values also have that CPU cost because a lot of the computation for what needs to be stored on disk has to happen at index time. So we took all of that out of sort of the default template and created our own. And it actually, like I said, at the bottom, this change, it dropped the CPU cluster, the CPU usage on an Elasticsearch cluster reasonably noticeably. I guess 25% to 15%. I'll take that. the message complexity that you send to Elasticsearch, again, it makes a big difference. If you're sending 1 million log lines that are a kilobyte versus 100,000 that are 10 kilobyte, Elasticsearch is going to have to do a lot more work on those larger log lines. In this case, we started sending a bunch of log lines that were 20 kilobytes, and you can see like the pretty clear impact that it had on the Elasticsearch cluster. The indexing rate just went through the floor because of the amount of work that the cluster was having to do. And then breaking those log lines down into smaller log lines actually just brought the performance back up, even though we were indexing more. So try not to send really big log lines. Sometimes, though, your applications generate really big log lines, and it's hard to necessarily break those down at the source, and maybe you need a bit of a fail-safe. We have this little bit of code in our Elasticsearch, in our Logstash configuration, which just chops off log lines at the 10K point. And this was a huge help. You can see the 2 arrows there before we did that and after we did that. We talked to our developers and we said, look, if we have these really long log lines, how often are you actually looking at the 500th kilobyte of a log line? And every single one of them said, no, we really don't. That stuff shouldn't be happening. It's kind of an accident if it does. So we just decided to chop off all log lines at 10K, and it helped our indexing performance quite a bit. Not only that, it also helped the Logstash performance. Logstash now has to do a lot less work, so it's able to spend that CPU doing other tasks, other kinds of filtering, and your throughput goes up across the board. All right, we have 10 minutes left now. I've only got 7 slides. Thank you, everyone, for bearing with me. Index size definitely comes into play. Elastic recommend, actually I'll get to what Elastic recommend in a moment. If you're logging to multiple indices on the same sort of Elasticsearch node, first of all, try not to do that if you can, because Elasticsearch has to split that index buffer between every active shard that it's writing to. So if you're only writing to an index called logstash today's date, that's fine. But if you are telling Elasticsearch that maybe you have many different kinds of indices that you're trying to log to, try not to do that if you can avoid it. But if you have to, do the thing with increasing the index buffer. When I say Elasticsearch has to split that between every active shard, an active shard is any shard that's had writes go to it in the last 5 minutes. So if you have 100 different indices across your cluster, you don't have to worry about all of them as long as you're not writing to all of them. One of the little things that we had to do when we were spinning up the cluster, we started ingesting a lot of syslog logs, varlog messages, varlog syslog, that kind of stuff. And what we found was, on a number of boxes, logrotate hadn't been running successfully for months. And these log lines, stretch back like 6 months, a year. And when we started sending them into these guys, I got my teammates at the front here, they're chuckling because they know what's about to happen. When we started sending these to Elasticsearch, suddenly Elasticsearch had to create 360 indices very, very quickly. And just, it brought the cluster down. So one of the little tricks we did was we made our own date filter, which parsed log lines, and if the date extracted from the log line was more than a certain number of days old, we would send it to a separate index. And we could then go back and take a look at that later, see if we actually cared about that log line or not, given that our retention is only 30 days. But that was one of the cases where Elasticsearch, when it creates a lot of these indices, they're all new. It has to split that index buffer between all of them, and the indexing performance just goes through the floor. So try not to index a lot of very old data across many, many indices at the same time if you can help. Okay. Like I mentioned already, tune the refresh interval. 1 second is really way too frequent. Cool. And then the last thing, when we're talking about SSDs, Different SSDs have different amounts of buffering that they do before they write to disk. So most good enterprise SSDs that we've worked with so far, they have two layers of kind of buffering. The first is they will buffer things to DRAM on the actual SSD. And the second is that they will usually write to some kind of scratch space on the silicon before actually moving the data to where it needs to go. Good SSDs and the latest Samsung line, ones that I have experience with, but the latest Intel line is also very good, have large amounts of DRAM and large amounts of scratch space on disk, and they have power capacitors so that in the event of power loss, you're not going to lose anything that's in DRAM. These are the kinds of things, if you're buying SSDs, that you need to think about because it will help your performance quite a bit. And with that, I have squeezed 2 hours of content into an hour and a half. Thank you. Questions? Yes? Anything on the Logstash shipper, for example, FileBeat, any performance improvements, anything you need to think about? Versus syslog. We are still using Lumberjack from like 2 years ago because we made a number of improvements to it locally to add things like high availability and some resilience and bug fixes way back when. I would recommend using FileBeat these days. It is really good. If you're scaled up and you have multiple Logstash instances, FileBeat can load balance distributing your logs between all of them, which is much nicer than, for example, if you have something else like certain syslog packages, which will only send to like one at a time and then fail over to the other and fail over to the next one. So distributing that stuff, FileBeat is very good at that. Yes, I do recommend it. Yeah. You had a question? Two. Go. So the question is, when you're talking about active shards, does that mean you have one shard per index? No, per host. Yes, one active shard per host. That's what that was the baseline that we started with. We scaled out the number of boxes so that we would have actually one primary and one replica per box. Actually, it was a little bit less than it worked out to like 0.9 because we wanted to have the ability to like lose some nodes and not go below this limit of one primary and one replica for today's index per host. Elastic recommends not having more than about 30 to 50 gigabytes per shard. So once we got to that point, we had like that stabilized. We ended up increasing the number of shards that we had on each box. So then, increasing the index buffer accordingly. So when we went through the process of benchmarking, we increased the number of active shards. We saw that there was a bit of a drop in performance. We increased the index buffer until that performance came back up, and that's how we knew we were at a good point. Yeah. Second question?
Well, so as a carry on from that, so that implies that you actually have two active shards, because the replica is still technically an active shard, still receiving writes.
Yes. Yes, so the follow-up is that implies you have two active shards per host. Yes, yeah, we have two. Like it works out to like, for us it works out to about 0.9 because we wanted to be comfortable losing about 10% of our nodes. And not losing necessarily in the sense that hardware fails, but losing in the sense that we may need to pull out a number of these hosts to do maintenance on them, to upgrade OS, to do any, replace SSDs because we burned them all out again. Things like that. So just having that buffer, that's kind of where it worked out to, yeah. Any other questions? One, yes?
Yeah, you were saying that it was a good idea to just spread out your compressor Logstash to the Elasticsearch node.
Yep.
So is that something that Logstash lets you do, say that you put that in a load balancer?
Sure. So the question is, when you're talking about splitting indexing from Logstash into your cluster, having Logstash sent to multiple different nodes, do we use a load balancer or do we tell Logstash how to do it? We don't use a load balancer in this case. Logstash does a pretty good job of it. You can tell Logstash to use multiple Elasticsearch nodes We haven't actually tried doing that because what we did initially worked really well, which was just to have each Logstash instance indexing to a different Elasticsearch host. And we just used our configuration management to make that allocation happen. And it works very well for us. But Logstash, certainly in the newer versions, you can tell it to, you can give it like a list of Elasticsearch nodes and it'll kind of try and balance that out. Like I said, I haven't played with it. I believe it works reasonably well. But no load balancer in the middle. Do I have a link to the custom mapping? I thought I had put it in here. I don't, but what I'll do is I'll tweet it out this afternoon so that everyone can see it.
Doesn't it say you have a use case where all this data that you are putting in your, let's say, cluster, you generate alerts from it, and do you use watchers for it, or do you have a recommendation?
So, sure. So at Etsy, do we alert on the data that's in Elasticsearch, and how do we do it? Do we use Watcher? Do we use something else? We do generate alerts, monitoring alerts, various other kinds of alerts, performance and so on. From the data in Elasticsearch, we don't use Watcher, and mostly because Watcher, for the size of cluster we're using, it was cost prohibitive for us. Instead, we rolled our own solution called 411, which I believe we have open sourced at this point. I think so.
Elast Alert open source project?
Huh?
Elast Alert is an open source project from ELK.
Okay.
They use that, and I'm just trying it out, and
Yeah.
really want some recommendations on it.
Yeah, I mean, if there's, I would recommend, the one thing I've found with the community stuff from people using Elasticsearch is that it's really good to try out different things. Everybody likes a slightly different thing. That's why there's, you have two plugins like Elasticsearch Head and Elasticsearch Kopf, which do roughly the same thing, but different people like different things. It works with different people's workflows. Do try out, try that out. I'm reasonably sure that the thing that we're using is also open source. If it's not, I believe we're working on it, and it should be out soon. But so we end up rolling our own solution as well. And I believe that's not an uncommon thing. I believe there are several places who end up doing this. If you can afford Watcher, it is really nice. I've played around with it a little bit, but for our cluster size, it wasn't an option for us. Yes. How do we retire the data? We have a script. So there is a Python package called Elasticsearch Curator, which is out, that I recommend people use for retiring old data. You can run it on a nightly basis, and you can tell it to just delete data over a certain age, and you can also tell it to move your data from one set of nodes to another, and it's sort of the recommended way of doing that. Internally at Etsy, we wrote our own tooling to do that, but that was before Curator was available, and before it did all these things. But Elasticsearch Curator is the tool to use for doing that. You can just specify whatever archival policy you like, and say, after a week, move my data over to this older node. After a month or 2 months or whatever, delete all the older stuff. So that works pretty good. Any other question?
What are your thoughts on using a queue?
Using a queue in Logstash like Redis, kind of as a buffer between things, I'm not a big fan of it. I know it is something that Elastic recommend. I'm really not a fan of it because we've tried it 3 or 4 times, and every time we've tried it, what we've gained has been outweighed by the latency it adds to the pipeline. It was nice to have, we tried using RabbitMQ initially as a buffer. We found there were bottlenecks in that. We got over the bottlenecks, and it was good because it added a little bit of high availability. This is going back 3 years now, when we started using Lumberjack, and it could only send logs to one Logstash instance at a time. If that instance went down, you'd end up with a cascading failure, and you'd thundering herd all your Lumberjack instances. all your lumberjack connections onto like one box, that would go down, they'd pile onto the next one. So in that case, like 3 years ago, it was kind of helpful, but these days with file being able to handle high availability and failover more gracefully, we find that the most it really does is it adds latency, and we don't really gain a whole lot from it. So there is one use case I did hear about though, which I thought was really good, where a company had a network partition, like they had a secure environment in one place, and their ELK stack ran in another. And so they had their logging from the secure environment go into a single queue and then get pulled off of that. Which is, and I think in that case, it actually makes a lot of sense. Like that's a constraint that you're working within. But in other cases where if you don't have something like that or a reason to necessarily do that, I don't find that it helps a lot. Yeah. Okay, and we're done. Okay, at the back they're telling me we're done. Thank you, everybody.